Hello everyone, I welcome you in this lecture, and in this lecture we are going to talk about KMP algorithm for string matching. KMP stands for not more spread algorithm. This is the name of the person who proposed this algorithm. This is one of the very efficient algorithm for string matching. So far we have discussed about naive string matching, which is a string matching based on the brute force approach. Though the naive string matching is very straightforward, very simple algorithm, but the drawback is it is very time consuming and it's very costly algorithm. We have seen that when we work with naive string matching, after doing lot of uh, valid comparisons, means when many of the patterns characters are matching with the text characters, and once you get a unmatched character, then in the next iteration you start again from the very beginning, and this takes a lot of comparisons. Now in the KMP algorithm, all these matched character will be utilized to skip some of the comparisons, and overall we are able to reduce the time complexity. So let us see that how the KMP works and how this algorithm is said to be efficient algorithm. So let's start. When we talk about the string matching, our objective is we need to search a pattern in the given text. So we are provided a pattern. Pattern is a sequence of characters, and we want this sequence character to search in a given text. Now the idea of the KMP algorithm is very straightforward, and also it seems to be very efficient. Let us see the idea first, and then we will go to the formal algorithm. So after some characters matches of P with T and then a mismatch, the matched Q characters allows us to determine immediately that certain sets are invalid. So in the previous algorithm of naive string matching, we have find that uh, after some of the characters of the P matching with the T, and if any of the characters which is not matched with the T, then we efficiently assume that the shift is invalid, and we start the process again with the very next character. What does it mean? It means if you are provided a text of this is some text length, and then we have a pattern, and this is, let's say this text is composed of these characters, and this is our pattern which is composed of again these characters. And what we have seen so far, that let's say these characters are matching, this is matching, and this is a mismatch. So once you find a mismatch, we say that this is an invalid shift, and in the next iteration we simply shift the pattern with next to the one position, and we are not utilizing any information about this matched character. Now the KMP says that whenever you find a mismatched character after getting a series of matched character, then in the next iteration we can utilize this information so that we can skip some comparisons which are not required. Now this is a basic idea. Now how this is achieved, that we have to see here, but KMP says that whenever you find a, a scenario where many of the characters are matched, then definitely we will get some information out of this matched characters. Okay, so the match characters in T are in fact prefix of P, and this is also very sure that whenever you find some characters are matching, these characters are definitely a prefix. Prefix is a substring of any string which starts from the beginning. What does it mean? It means if I say A, B, C, D, E, this is my string, then my prefix is any substring which starts from the beginning. Means AB is a prefix, ABC is a prefix, ABCD is a prefix, A itself is a prefix. So definitely when you find some of the characters of the patterns matches with the characters of the text, then definitely these characters are a part of the prefix or a prefix. So it is determined whether a shift is valid or not, and with this prefix information which are getting matched with the text, we will easily find out that the next comparison or how many characters we have to shift, uh, because there is no need to shift one by one character. We can immediately find out that how many shifts are invalid. Define a prefix function pi. So here we need to create one function pi. Actually, this function can be used as a heuristics to get our solution. So in this KMP, we have to create one function that is called prefix function pi. It is in the form of table. So we have to create one table, and this table will actually guide us that how to proceed for this pattern matching, which encapsulate the knowledge of about how the pattern P matches against the shift or itself. So the very first thing is, whenever the pattern is given to you, so we are going to make one prefix function for this pattern. So one thing to keep in mind, that this we are creating, this is a kind of table this which we are creating for our pattern, and this table is actually guiding us that the whenever any unmatched character is found, then the next how many characters will be give you a valid shift. Now this prefix function, this pi, this table is of size m ranging from 0 to m minus 1, and keep in mind that m also denotes the length of the pattern. So this table will be of the size of the pattern which we are going to search in the given text. Now how to determine the value of this pi? So pi is basically an array, you can say, of size of the pattern. So pi of q, how the value of each entry of this pi of this table or this array can be determined. It can be determined by using this definition: maximum k. So here we are writing the values which we are calling as k, such that k is less than q. So now keep in mind that q is actually the the number of matched characters. So here we out of m we are having some characters which are matched with the text, we are calling it q. So obviously q will be less than equals to m, and k is now less than q, such that this p of k as matched is less than equals to p of q. So k is some value which we keep on calculating, and the value will go up to the match characters of the pattern in the text. That is, pi of q is the length of the longest prefix of p, that is a proper suffix of pq. So each entry of this prefix function is actually telling us that at any instance what is longest prefix that is matching with the proper suffix of a given pattern. What does it mean? It means if I say a a b a a, so here you can see in this particular given uh, string, here we have uh, this is your prefix and this is your suffix. So here you can see you have uh, k equals to 2 at any point, that will say that the longest prefix is also the proper suffix. If I say, if I add one more a here, then in this case now we have a longest prefix which is also the proper suffix, means this part is actually matching, and the size and the length of this is 3. Similarly, if I write this a b c d e k a b, so here you can see this is your prefix, this is your suffix. So here I can say that the longest prefix is of size 2, which is actually the suffix here. So this is how we need to represent this value, and how to get this value, this we will see with one algorithm. So let us go to the formal algorithm. Now if we talk about the KMP algorithm, in the KMP algorithm, if you have a look, we have some steps, and in these steps we will find one term, compute prefix function. Now compute prefix function is activity to determine what is this prefix function for any given pattern. So first you need to know that how to compute this, and once you understood that how to compute this, then we can go with the KMP algorithm. So let us first learn that what is compute prefix function and how to determine this. So first we will go to the algorithm of compute prefix function. So let's see here. Okay, so this is the algorithm for compute prefix function, and we are determining this pi representing the compute prefix function. It's a kind of sort of array, you can say. Okay, so the pi of 0 is 0. So there are some assumptions are there. So pi of 0 is 0. Input, what we need to provide? We need to provide a pattern. So one thing to keep in mind that compute prefix function is determined for a pattern. So we need to provide the pattern of length m, and what we will get as an output? We will get one table pi of size m. So m is actually the length of the pattern, and let we will take one array of size m. We are calling it pi 1 to m. We a new array pi of 1 equal to 0. So initially we will do some initializations. We will do some values, default values we will provide. So pi of 1 is 0, means the very first index of this 1 to m we are keeping as 0, and k equal to 0. So we are using some variables to do some task. So here we are using one variable k, and this k is initially 0. Now for q equals to 2 to m. Now if we talk about, if we take any string one, then this this is a string which is composed of only one character, then the suffix and prefix is having the same meaning. Then there is no need of determining that what is the longest prefix, which is actually a proper suffix. So we are not actually able to determine the prefix and suffix relationship in a string of size 1. So actually we will do a loop for from q equals to 2, means from the second character of our given pattern up to the last character. So q is actually determining the values that goes up to the size of the pattern. So our pattern is actually this one is our pattern. So this is one example also I am considering side by side, so that we can understand the steps in a better way. So here the pattern is this: a b c d a b d, and we want to find out the prefix function, or this particular table you can say, of this given pattern. So here 1 2 3 4 5, the size of this of the pattern is 7. So the q will go from 1 to 7. So there's a loop that will go from 2 to the 7 here in our case, while k is more than 0 and pk plus 1 is not equals to pq. So actually what we are doing, we are trying to compare the first value and the last value in order to find out that the longest prefix is also the proper suffix. This is actually our main idea to determine. So uh, if k is more than 0, now keep in mind that for q equals to 2m, we have a for loop. In the for loop we are doing this entire task, and after completing the for loop we are going to get this pi, right? And if the values does not match, then we are again in the while loop. Now which value does not match? We are actually matching the value of p of k with the p of q. If the value does not match, then we will in the while loop. If it is matching, then simply we will increase k equals to k plus 1. Okay, so let us see that what is happening. And after doing all these times, if they are matching, if they're not matching, finally we have to write the value of k into this uh, into this table, okay, or you can say into this array that we are actually want to get at the last. So we'll start. So k equals to 0 at initially, and q equals to 2. Now, while k is more than 0, that means because k is 0, this loop is not going to execute, means this while loop has no significance initially. So when you start working on this particular algorithm, this loop has no meaning because k is 0, and this loop is only works when k is more than 0. Okay, so we will be going here. Actually, we start from here. So k plus 1, k plus 1 means k is 0 means k plus 1 means k1. So when k of 1 is equals to, when p of 1 is equals to p of q is 2. So if p of 1 equals to p of 2 means if this value is equals to this value, then we increment the k. But actually these two values are not equal. So what we will do, we will simply skip this because this is only going to execute when this is true. But in our case, this is not true. So what we will do, we are going to write k equals to uh, pi q means whatever the value of k we are going to write in the value of in the q index of pi. So q is 2. So in the pi of 2 we are going to write k is 0, and also we have taken pi of 1 equal to 0. This is also 0. Now you will go back. K is still a 0 but q is 3. Now q is here. Now we want to compare. Now again, this is still uh, not more than 0. We will skip this part, and then we'll say pk plus 1. K plus 1 means we are comparing this value with this value. Is this same? No, this is not same. So what will happen? We are going to, we will skip this and we will write k equals to pi q means in this index q we will write the value of k. So k is 0. So in this index pi of 3 we write, because q is 3, so pi of 3 will be 0. Now we will go to the next iteration. Now q is here. So q is 4 and k is still 0. Again, what we will do, this is not going to execute. You go here and you compare. K plus 1 means k 0 plus 1 means you are comparing this. P of 1 is equals to P of 4. No, this is not 4. Again, we will do the same process. This is going to be 0 and Q is going to 5. Then we compare P of K plus 1. So means P K is 0. So P of 1. P of 1 is A. Is this is equals to P of Q? Now keep in mind this is still not executed because k is still a 0. So we keep on skipping this part, and we actually now this condition got true because p of k plus 1, k is 0. So p of 1 equals to p of 5. This is true. Now when this is true, what we are going to do? We are going to increment the k. So k is going to become 1. Now what we'll do, when k becomes 1, we will write this value of k into pi of q, and q is 5 means q this pi of 5 we will write the value of k. This is 1, and then we'll go to next iteration, and then this is 6. Now k is already reached to 1. Now what we will do, we will see that this uh, p of now 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 because we have already value of k equals to 1, so now we will see that this loop will work or not. So here you can see k is more than 0. Yes, k is 1, so this condition is true. But for this loop to execute, we have to satisfy two conditions. K must be more than 0, this is true. But p of k plus 1 must be not equals to p of q. So p of k plus 1 means p of 2 means this value should not be equals to this value. This value. So actually these two are equal. That means again this while loop is not going to work, and we are here. Now here you can see p of k plus 1 means p of 2 is equals to p of 6. Yes, this is correct. Then we are going to increment the value of k. So k becomes 2, and whatever the value of k becomes, that value we are going to write in this index. So here we will write 2, and then we will go back, and now this becomes 7, and this is the last uh, actually index for this loop. This is the last value to be executed. Now k is 2, so we will again check what is the status here. So if you look here, k is more than 0. Yes, this is correct. but to execute this part we must satisfy the two condition. P of k plus 1, k plus 1 means k is 2, k plus 1 means 3. So P of 3 means this value. This value must not be equals to P of 7. Yes, this value. So let us make it more clear. So Q is here and k is 2. So we are comparing k plus 1 means P of 3. This value must not be equals to this value. Yeah. So if these two conditions are true, this will be true. Means the conditions are true, we go to this part. So what you will do, k equals to pi of k. Whenever you got this condition true, then we will assign the value k the pi of k. Now what is k? K is 2. So pi of 2 is what? 0. So you will assign k equals to 0. So k will be again becomes 0. Now because the while loop, you go back again and you check the condition is true or not. Now it becomes false. So you skip this part, you come here and now you will check pk plus 1. K is 0. So k plus 1 means p of 1. P of 1 means a. Then you compare p of 1 with p of q, p of 7. Now this is also not equals. This will not execute. So you simply assign here k equals to pi of q. So k is what? 0. We will assign to pi 7 will be 0. And then when you go back, this loop got finished and it will return this function. So this is what we get. Now with the help of this uh, prefix function or this prefix array, we are able to do our pattern matching in a faster way. Like in the naive string matching, with every unmatched character, we are simply repeating the same process again. But now we will see that how this array is going to help us. So let us move next. Okay, so now I assume that we have actually understood how to work with the with the compute prefix function. We will quickly take one example just to recall all the steps. Now, one thing to keep in mind, in the previous example, it says 0000120. So 00001. Now, what is the meaning of this? This actually pi of q. So the meaning of this is when you write A, B, C, D, this is a string, then you will find that there is no prefix which is actually also the suffix. But when you write A, B, C, D, A, now you will find here that we have uh, uh, a string of size 1 which is actually the prefix and also the suffix. Yeah, now you can see here, if you look at this entire string, you can see the longest prefix is also the proper suffix is of size 1. This is the meaning of this. Now if I write A B C D A B, now you can see the longest prefix is also the proper suffix. This is what we are getting from this information. But if you write it A B C D A B D, now this is 0, means there is no prefix which actually matches with the suffix. So this is what the actually the significance of this particular all calculation. Now if I do it quickly, so if I say my pattern is A B C D A B C Y. Now already we have seen that how this algorithm is executing, but now I'll do it quickly. So if this is my string A and B, then there is um, no string for which there is no substring for which the prefix and suffix are matching. But if I take this one, if this is my string, then again there is nothing. If this is my string, then also there is no prefix and suffix. But if I take this one, then if you can note here that A B C D A, that means we have one size prefix which is also a suffix. So here the value is 1. Now if you go up to this much, A B C D A B, so we can see that how the values are coming. Now this is actually 1. Now if you look at this string, this will 2. That means this is a prefix which is also the suffix. If you see C here, then you can see that this is a longest prefix, which is also the suffix. So here you can 3. Now if you write y here, then there is no prefix match with the suffix. This is 0. So this is the entry for the pattern. For this pattern, this is our pi of q. So I hope that you understood that how we determine the prefix function. Now we will use this prefix function to uh, do the pattern matching. So let us go to the formal KMP algorithm. Okay, so this is our KMP algorithm, which is actually used for string matching. So far we have discussed about a subpart of this algorithm, that is a compute prefix function. So let us see that how the things will work. It is actually very much similar. The overall approach, if you look to it, you will find that uh, the core idea is actually based on this compute prefix function. So in this, what is required, whenever you want to do string matching, we need to pass two things. One is the text into which we need to find the pattern, and the pattern itself. So we will provide two input, the the pattern of length m and the text of length n, and we are assuming that m must be less than equals to n. And what you will get, list of all numbers s such that p occurs with a shift s in t. So in the output we will find that we are able to get that the pattern is found or not in the text. N is the length of the text, m is the length of the pattern, and this pi is representing a function. We call it as a prefix function for this pattern. Already we have discussed. Then we use uh, variable q, which actually guide us that how many characters have been matched in the text, means how many characters of the pattern is already matched in the text. This is the meaning of q here. So initially the q is 0, means so far there is no characters has been matched. Now we have to uh, do some exercise for the entire text. Now that the text size is n, so there's a loop for I equals to 1 to n. So here text is actually an array of size n. So text is representing your string into which we are looking for the pattern. While q is more than 0 and pq plus 1 is not equal to ti. So if this represent the character is not matching with the text character, then you have to uh, decide what to do with the help of this prefix function array. If it is matching, if the character, if the pattern character is matching with the text character, then you have to simply keep on comparing each characters. So in this loop we are just comparing each character wise into the pattern, and here we are doing that if the character is not matched, then what to do, means how to proceed with the help of the this prefix function array, what to do. And finally we are also checking throughout this process if q equals to m. If you find that q is the number of characters which is are matched. So if number of characters match equals to m, that means the entire pattern has been found. So if you find that q reaches to the value m, that is the size of the pattern, you will say that pattern is actually matched. And at which shift it has been matched, that is also can you find out by using this I minus n. So let us take one example to understand in a better way. Okay, so this is the algorithm given to us. This is KMP algorithm. Already we have discussed. Now this is the prefix table. So we are assuming this is a string. This is the string given to us. A B C D A B, and then we have a space. This is a space is also acting as a character here, and then this is the entire means string. And the pattern here is this one A B C D A B D. This already we have discussed. So the prefix table for A B C D is 0 0 0 1 2 0, and we discussed that how to get this table or get these values. Now we will use this KMP algorithm to determine that the pattern exists or not. If it exists, at which shift it actually exists. Okay, so let us uh, take some variable here. So q equals to 0, right? Q is actually used to find out or actually represent that how many characters have been matched here. Okay, for I equals to 1 to n, so this is I. While q is more than 0, so initially q is 0. So as we did in the previous computation, that this while loop will only work when q is more than 0. So initially when you start, this is going to be skipped because initially we have q equals to 0. So definitely this part is not actually meant for the initial steps, but later this will be useful for determining. Again, to remind you that this is actually helping us with the help of this prefix table, that how to proceed if a unmatched character has been determined. Okay, so if q plus 1 equals to t of I, now q is equals to 0 initially and I equals to, you can say, 1. So I is actually this one, right? So we are comparing q plus 1 means we are q is 0. So we are comparing p of 1, the p of 1 and with the t of 1. So if it is matched, yeah, it is matched. If it is matched, then we will say q equals to q plus 1. So q is going to increase 1. Okay, now, and also we will check if q equals to m. No, q is not equals to m because q is only 1 now and m is actually 7. So m is the size of the pattern. So this is not true. So we again go back to the for loop and I becomes 2. Then you compare q plus 1. So again to remind that while loop will not, just a minute. Now here you can see that initially the while loop is actually not executing, but now the value of q is now becoming 1. So yes, we have a scope to look into this statement. So this is true. Then q plus 1, q plus 1 means q is actually 1. So q plus 1 means 2. So p of 2 means we are comparing this p of 2 with t of 2 because I is also 2. So we are comparing this. So if both are true, then this will not work. This will only work when this is not matching, when this is not equal. So this is not going to execute. We'll go to the next part. Now here see if p of q plus 1. So p of 2 is equals to t of 2, then q will increment. So actually here q will become 2 and we go to the next iteration because this is also not work, 3. Now you can see here actually if you look at this pattern, so every time this is going to be skipped because this is going to be false. This is only have a meaning when your character is not matching, but if you look here actually your character is matching. So every time what is happening, uh, now this is also matching, this is also matching, so this becomes 3 and I goes to 4. So now this is I is here and q is here. So we always compare the next character. So means q plus 1 means 3 plus 1 means 4. We are comparing this and this, again is match. So q becomes 4 and this becomes 5. Okay, so again we will compare this and this. This is also match. So this becomes 5 and this becomes 6. Now keep in mind that uh, q is actually here and sorry, q is actually at the value 5 and I is here. So again when you compare, this is matching. Now keep in mind this is actually q, this is I, and we are comparing that q plus 1 does match with t of I. Yes, it matches, so it becomes 6 and this goes to 7. Okay, so here I is here and q is here. Now we reach to the situation where we can see that while is going to work. Now while q is more than 0, yes, q is actually 6, it is condition is true. P of q plus 1, so q plus 1 means this one, 7. If this is not equals to this, now this is actually space and this is d, which is not matching, so this is true. When this is true, then we will assign the value of q to the pi of q. So pi q is what, 6. So pi of 6, we have to look here. and you will see that pi of 6 is what? Pi of 6 is 2. So that means we are assigning the value q. So now q is actually becomes 2. Now, actually, what is the meaning here? The meaning here is, if you look at this at this point of time, if you look the string just previous to all the characters, you will find that actually a and b, the suffix is also the prefix. That's why we get 2. That means we are able to skip 2 comparisons in the next iteration. So now you can see here q becomes 2. Now, because you are in the while loop, so still you will go and check the condition is true or not. So q is more than 0. Yes, q is more than 0. This is 2. And q plus 1 means p of q is 2. So p of 3 compare with p of 7. So p of 3 is this, is not equals to p of 7. Again, this is true because this is c and this is space. Again, this is not matching. That means the condition is true. We will go here and we look to pi q. Now what is q? Q is actually 2. So you'll go to pi 2. Pi 2 is 0. That means q, you will assign this value to q, then q equals to 0. And the moment the q becomes 0, what you will see, you will be out of this while loop. So actually only you did two, with the two comparisons, you are able to compare the entire 7 characters. Okay, this is what it says. Now if you look at this loop is actually now not true. We're not going to execute because q becomes 0, and for q equal to 0, this is not going to execute. So you will go and check here. Now pq plus 1, q is 0, so p of 1 is equals to t of 7. So p of 1 is actually a, and t of 7, this is not matching. So simply you will skip this part. Nothing is going to happen. You are not going to increment the q, and then you will be going back, and this I becomes 8. Now keep in mind, at this point of time I is 8 and q equals to 0. So now this is not going to execute because q, it will work only for more than 0. You come here. Now again you compare. P of 1 means this is matching with this. Yes, it's matching. So what you will do, you simply increment the q. So now q will be 1 and I will be 9. Okay, now again you will compare this and this is matching, so it will increment the q and you will increment I. So I am just doing it fast because we have understood that how the things are working. And then what you will notice here, this is also now I is here and it is matching with this. So just a minute. Now look here, I is 10 and q is 2, this, and we always compare with the q plus 1. So now we compare this and this, which is correct. That means correct means they are matching. So you will increment q equals to 3 and this will be going to 11. Okay, now you are here and now you match this d and this is again matching. Q will be 4 and this will be 12. Now this, and you will match this is matching, so q will be 5 and this will be 30. Okay, now here, so q will be 5 means you will compare this and this matching. You will q will be 6, will be 14. Now q is here. Now you will see here, no, now if you look here, we have so far skipped this part because this is all matching. Now if you go back here, q is more than 0. Yes, q is more than 0. Q is 6 and q plus 1. Q plus 1 means this is not matching with this is not matching. That means this condition is true. Then what we will do, so whenever you find an unmatched character, then only this while loop will work. So just keep in mind, because we have unmatched character, we'll go here and then we'll decide what to do. We'll take help of this table. So pi of q, so q is what? Q is 6, so pi of 6 is what? 2. So we assign the value of 2 to q, so now q will be 2. Still the condition is true, and then we will check the pi of q, this p of q plus 1 means p of 3. So p of 3 is what? P of 3 c will compare with this 14. So this is actually matching. This is actually matching. So this condition is not going to work. So we will skip this part and we will go here. Now you see here, if this is matching, then what will happen? We simply increment the q, so it will be 3, and this will be what? 15, and then this will be 15 is there. Then you will match d, and d is matching. So 4, this becomes 16. Then a and a will be 5, and this becomes 17. Now let me clear this. So q is 5, q is 5, and this is 17, and every time we are comparing q plus 1, so this compare with this is compare matching, so we'll again increment 6, and then it is here. Now this is ad, and this is, and you will compare q plus 1 is 7 and 7, this is matching, so this becomes 7. Now it goes to increment 19, but before you go to this, what you will find, whenever you find the q, because every time we are not actually discussing this part because we have already skipping this part, but now this part is not going to skip because q becomes 7. The moment q becomes 7, that means your pattern has been identified. This is the pattern which has been identified, and at which position it has been identified, you will just find that it is I is equals to 18 and m is 17, so 18 minus 7, at 11th index you have find that this is a pattern. Pattern is matched means after the 11th, you can say, so that means up to here. From here means from the 12th you will find a b c d a b d has been find matched here. And now you go to the next index. The next index, this is one pattern has been found, and we are interested to find all such pattern in the given text. So it goes to 19, and in the 19, this is actually the last the this is actually the last index, you can say, for this entire loop. And whenever the pattern has been matched, whenever we found, we will set it, the q equals to 0. So once it is found, we will set the q equal to 0, and then again we keep on doing the same step. But in our case, this is actually the last index, so we'll stop and we will find that pattern has been found in this text at the index 12, and this is our answer. So I hope this is understood to you, and you have realized that now we have reduced many of the comparisons because we have simply skipped by using this prefix table. So this is the idea of the KMP algorithm, and now we will see that what is its running time, that how much time it will take, and how this is better than the previous one. This is the time complexity. So if you look at this, so the time complexity to be derived by using the two main things. One is the prefix function, which is the main component of this algorithm, and then the other steps of the KMP. So let us check that what is the cost of the prefix function. So here you can see that this is simply the assignment task, which is just calculating the length of. Here we are simply telling the length of the pattern. We are simply initializing some variables. Now for q equals to 2 to m. Now here we have a loop which is almost m minus 1 size, so we can say this is almost of size m, while k equals to 0 and pk plus 1 is not equals to pq. Now this is the loop which is actually this is the loop which actually works, but to keep in mind, whenever you find the status where the longest prefix is also the suffix, then it will be maximum uh, of half size, uh, actually less than half size, because if I say A, B, A, so definitely it is of a string of size 5 length, and here you can see this is actually 2. So you cannot get any kind of this value which is actually more than half. Okay, and that too, this is only working uh, of half size when they are matching. But if they are not matching, means if the skin is of random, then you will be doing this kind of unmatched situation, maybe of some constant time, which is very much less than even in half. So here, if you see this while loop is only executing when you will find the unmatched character after a series of matched. Means actually here we are going to find out the longest prefix of the same suffix size, which is actually of some constant uh, efforts are required in this loop. So we can just take it some constant value for this. Now if you look here, if you look to all the steps, either you are going to use this or you are going to use this, because they are just uh, mutually exclusive. If this is executing, this will not execute. If this is execute, this is not executing. So that means the overall impact is we are actually using or running to m times. So the overall execution or the effort that actually required for this function is m times. So we will say this is theta of m. Now coming to the KMP. In the KMP, in the initial steps, we are simply doing some initialization work, which is of constant effort. And if you look to this statement here, we say that this is the cost of theta m, which already we have discussed here. Now in this part, we have one loop which goes to n time, and if you compare this analysis with this analysis, you will find this is almost of the same kind. Here we have a loop, and here we are actually doing a while loop, which actually again work with the mutually exclusive this statement. Either this will work, either this will work, and uh, the execution will be definitely very much less than the half even. And if this is working, this is not work. If this is working, this is not work. So the overall execution, you can say, or the overall execution of these steps will be taken n times. So the dominating factor or the dominating term that actually defines its execution will be defined by this for loop. So all these terms are actually, you can take it as a constant effort, and these constant effort are applied by n times. So the effort will be theta of n time. So if you talk about the total cost, so the two dominating things that we are doing, one is done by this step and other is done by this step, and we need to calculate the effort done by these two steps. So this is m and n. So the total cost can be represented as a theta of n plus n, which is much better than the previous one, which is we have discussed using the naive string method. So here we have seen that how the algorithm can be improved by using this prefix function array, and the cost of the calculating the prefix function is also not high. It is only theta m. So the overall cost will be theta m plus n. So this is all for this KMP, and hope you have understood this, and also you have find it interesting. So in the next lecture, we are going to take some more string matching algorithm. This is all for this lecture. Thank you very much.